Not the, okay.
Good morning, good afternoon, good evening, wherever you are or whenever you might watching this. I am honored to welcome you all in today's lecture. This is our second lecture in the machine learning series, and I am honored to have Dr. Khalid again, who has rich experience in machine learning and computer architecture. Dr. Khalid, welcome again, and you have the floor.
Thank you again, Dr. Salim, for the very nice introduction. And let's jump into it. So, in today's lecture, we will reinforce the concepts that we have explained in the previous lecture, and we will also build on them. And I would like to say that by the end of this lecture, we will have covered all of the math necessary to understand how neural networks are trained. So we would like to stress again on the idea of the rate of change. If you remember the great company Sun Microsystems, the creators of Java, they had a very famous saying that says the network is the computer. And from there, we build our slogan for this lectures, which is machine learning is the rate of change. Now let us proceed. So we'll start by describing minima and maximum. Any function, it has minimum points and maximum points. There is local minima, there is local maxima, there is minimum, and there is maximum points.
So, Dr. Khalid, can you elaborate more? What's the difference between the left and right figure? So there is a local max, local min, and in the right one there is a max and min. Can you elaborate more?
I think that's a good question, Dr. Salim. You're paying good attention. The difference between maximum and minimum here will refer to the global maximum. I mean, this is the highest value the function will ever reach in the range. A local minimum, sometimes a function like in life, you go a little bit up and then you go down. So that turning point between going up and going down is called a minimum or a maximum regardless of it is a global or not, and you can continue growing up. And if that turning point turns out to be the highest point, that's called the global maximum or the global minimum. And these our target of optimization in our machine learning series. Now, we also explained, or as you have seen previously, that as we approach a minima, the rate of a change keeps decreasing and decreasing. And you might not like the idea of the instantaneous rate of a change. You don't have to like the instantaneous rate of a change. Imagine that the period is one to make it easy and simple. In this diagram, we took a period of one. So the rate of a change with respect to a period equal one is decreasing and decreasing and decreasing as we approach the 0, 0, which is the minimum point for this function. Now, let us go back and again to the idea of the instantaneous rate of a change. The rate of a change means a quantity changes with respect to another quantity. For example, how your productivity changes over time. For example, in the example of the Intel grade level handbook we described in the previous lecture, how many tasks you accomplish per year, but how many tasks we're gonna accomplish per month, per week, per day, per minute, per second, per millisecond, per nanosecond, per picosecond. So the idea is shrinking this interval until it is close to but not equal to zero, and this is leads us to the idea of the first derivative. So there is a concept of limits that we will explain in this slide. For example, we have f of x equal x squared. How do we actually find the derivative for this function? Basically, we apply the limit, which is you see h here as h approaches 0, f of x plus h minus f of x over h. Again, h approaches 0 as we have described in the previous slide. Now, we're just gonna apply this x plus h to the squared function, and we will get actually this x squared plus 2xh plus h squared minus x squared over h. Dr. Salim, can you actually help us from here uh, simplify it to step 3?
Okay, so the step three will be 2xh plus h squared because x squared minus x squared will cancel each other. So yeah,
That's perfect. You are paying attention. I like that. I hope the audience also is paying attention as well. And you see now we do simplify it until we reach 2 of x. So that's here just a pure algebra. And we reach to the end as 2 of x.
so can you explain why we have f of x plus h, the first function?
Yeah, so the idea is again, we are taking, we start with an x, right? The idea is taking the rate of a change with respect the idea of a rate of a change over a period of time, right? So here it is a rate of a change. The starting point is x, and the ending point is x plus h. So how do you actually do take a rate of a change? You take over a rate of change over a period. You need a starting point and you need an ending point. The starting point is f of x, is x, and the ending point is x plus h. And you take their values, f of x plus h minus f of x. And then you just apply the square function into that. Is it clear?
Yes, yes.
So again, we do apply, we have a starting point, we have an ending point. The starting point is x, the ending point is x plus h. And as we said, h here represent the change. As we said, like how many tasks you accomplish per second, per millisecond, per microsecond, per nanosecond. And we need to calculate the rate of a change as this change in time is almost zero, but is not exactly to zero. So we plug in this in the square function and we calculate the instantaneous rate of a change. And as we actually factor out and reduce, we get 2 of x. Before we continue, let me actually put this up here so that does not blur the content. Okay. Now let's go to the yeah, Dr. Salim, you have a questions here?
Nope, nope, everything is clear.
Okay, so sometimes you in the diagrams or graphs of functions, you are gonna see an arrow, and this arrow actually represents the rate of a change or the instantaneous rate of a change or the gradient, if you will. And we're just gonna explain this quickly because you will see a lot, and it's a good idea to be able to understand what it means on the graph. This is the starting point, and this is the ending point. And here we move from the starting point to the end point. And if you draw a line that's perpendicular, that is parallel to the y-axis or perpendicular to the x-axis, that's called dy. And also a line that is perpendicular to the y-axis called dx. So basically we have a right triangle. We have this represents dx and this represents dy. So basically the rate of a change again is the change of y over the change of x, and this gives us the tangent of this angle. So technically speaking, this angle represents the tangent of this angle represents the rate of a change. So that's why you see in diagrams, they use these arrows to represent the rate of a change. And if the rate of a change is, if the arrow is parallel to the x-axis, that means the rate of a change is zero. If the arrow is pointing up, that means the rate of a change is almost infinity or infinity. And as the arrow points points up, or like the angle increases, the angle with the x-axis increases, the rate of a change increases. So let's take examples of some functions and their derivatives. We have, for example, the exponential function, which is e to the power x. Its derivative is e to the power x. And we can see here as we start, the rate of a change is, even the rate of a change is increasing because the rate of a change is proportional to the value, like to the value of x. As you go, as x increases, the rate of a change also going to increase as well. So the rate of change is going to keep increasing and increasing. So
So
let's,
I have a question. Can you go back? So this
yes,
is the function e to the power x, right?
yes,
And after the derivative, it's the same, right?
yes, this is a unique function, yes.
It's a unique function.
Yes, because the function is the same as its derivative.
I see.
Yep. Shall we proceed, Dr. Salim, to the next
Yes, yes,
slide? If you feel
yes.
free to ask any questions and interrupt at
Yeah,
any time.
yes, please. Go ahead.
Thank you, Dr. Salim. Let's now move to the derivative. Again, this is a sine of x, and the derivative of sine of x is basically cosine of x. Now, Dr. Salim, it's my turn to ask you questions. Can you identify any points of interest in this diagram?
Okay, in this diagram, the first one that we have a global maxima where
Yes,
is rate of change m equal to zero. So that's one.
perf perfect.
And we have minima when the m rate of change is decreasing.
Exactly. The magnitude of the rate of change is decreasing as we approach the global minimum. Thank you, Dr. Salim. That's a very good observation. Now, this is just another example of a function and its derivative 1 over x, its derivative is minus 1 over x squared. So this is just to give you, we're not going to go into the details of this function, just to give you details and a feeling of the first derivatives. Now, let's go to the concept of activation functions. We've described in the first lecture, or as have you have seen in the first lecture, that an activation function takes a signal, and this signal is a combination of multiple signals, and each of these signals have a weight. And this activation function produces a signal that can be either strong or weak depending on the input signal. And each of these features, if you call them features, they have different weights or they have different strengths in the way they affect the final signal. For example, if we're going to look at the research skills, the number of papers might be a very important factor in determining your research skills. And many people in the academia would already know that they judged by the number of papers they publish. And there's actually an adage they say is publish or perish. So let's go to the activation function, a strong signal. Here we just, for the purpose of giving an example, we have assigned random values and we emphasize that the number of papers is 25. And if you look at this light bulb, it's shining. The strength of the light is strong. And again, you see how each feature is multiplied by its weight and how the activation function is applied. And let's see, it's the same example, but we have tweaked a little bit the value of the research papers. And we've seen that once the research paper is 5, although this is 50 and the other attributes did not change that much, the light bulb got dimmer. So this is to show that attributes have different weights in affecting the value of activation. And this has also leads us to the how learning works. We are also stressing out how learning works. Once we know these weights, how each of these features, the weight of each feature, then we find our model. And that's what we'll be emphasizing again and again. Now, let's get into the idea of describing multivariate functions. So let's begin by describing what a multivariate function is by giving an example. Here we have z equal x squared plus y square. And another example is y equals z. You see here that, for example, this is the x-axis, and this is the y-axis, and this is the z. And Dr. Salim, do you have any comments or something here?
No, no, the z is the third dimension, right?
Yes, yes. Do you think this is clear
Yeah, yeah.
enough? Okay, for me, honestly, I don't see this is very clear enough. I find this diagrams confusing, and they might not convey the idea of multi-dimensions very well. That's why we will present multivariate functions or multidimensional functions in a more simplified way. In these examples here, we presented the third dimension as the height in this box. But Here, we're going to assume, again, for the purpose of simplicity, that the third dimension is the time. Now, since the third dimension is the time, we can see that at different time, the function might take on various shapes. We made up or we just concocted this multivariate function. At z equal 1, it's just f of z of x. So f is a function in terms of x and in terms of z. And it happens that we choose z to be the time, as we have shown here. See this nice clock icon. So at z equal 1, it's a squared function. At z equal 2 is just a very beautiful line, very straight line. And then at z equal 3, we have e to the power x. So Dr. Salim, would like to select any of these diagrams?
Yeah, we will go when the z equal 1.
Thank you, Dr.
So the
Salim.
first one.
Okay, we are gonna honor your choice and we would use that for the rest of the explanations in the slides. Also, for example, I might revert the sine function, but you like z equal 1, you like the squared function, we're gonna use that. We're not gonna let you down at all. Now, let's start with the multivariate function. So we select one variable as Dr. Salim has selected z equal 1. So we select this one and then we're gonna look at it further in the next slide. Now, once we have selected z equal 1, what is remaining? Now we have a function in 2 dimensions. We have the function f in terms of x only. So we have an x square function, right? And the idea of partial derivatives is not different from the idea of derivatives in 2 dimensions. The idea is that for all other variables in the function, we give them constant values and leave one variable without a constant value. So for example, when Dr. Salim selected z equal 1, again, when Dr. Salim selected z equal 1, this gave us fx of z in terms of x only. And now we are in 2 dimensions. And this symbol over here is called the partial, and that means this whole thing means the partial derivative of f of z of x with regard to x. It's just the only symbol that it changes. And again, we fix all other variables. We and give them constant values, and we only keep one variable without a value so that we write the original function in terms of that variable. So now we have x square and the derivative of this function with respect to x square is 2 of x, and we have seen together, and actually we have derived together the derivative of x square using the instantaneous raised to change in this presentation and also in the previous presentation. So this slide is very important. This slide and this slide also is very important. It shows that we have a multivariate function, and when we take the partial derivative, we have to give all variables constant values except one. And once we do that, we are left with a diagram or a graph that is in 2 dimensions. And once we reach this point, we can easily take the derivative. So the partial derivatives is not scary anymore, or does not look scary at all after that. So here is an example. So we explained in the previous slides, we have seen intuitively what does the partial derivative mean. Let's see it in action here and look at an actual algebraic example. So we have f x of z equal x squared plus z of x plus 5x. So this is a function that has two variables, x and z. And we mentioned that when we take the partial derivative, we need to set all other variables to fix. So when we set z equal 1, we get x squared plus 5x. There is a little bit typo here. We will fix it. Assume that this is 6x. And if we go here, when we take the partial derivative at z equal 1, it's 2x plus 6. So that is the nice idea of partial derivatives. It's just once we fix all other variables, we get a function in 2D dimensions. And once we reach there, we can easily take the derivative. Now, let's look together at the loss function. Again, we have seen that the loss function quantifies the difference between the prediction and the truth, or the prediction and the actual value. And we have discussed that why we need a loss function. We need a loss function to optimize our model. And what does it mean to optimize our model? Is finding the value of the weights, how the weight of each feature in the model. So the difference this time is that we're going to look at the loss functions, at the loss function in multiple dimensions. So here, how do we make a loss function? How do we create the loss function? So we apply the data set to our model. So we, for example, we have the first house. We apply it. We chose a linear model, and we apply the first sample that we have to our linear model. So we write that, and then we know the house was sold for 1000K, for example, and then the difference is squared. And we do the second thing for the third house, and we sum all together. The final function of these is a large function in terms of W0, W1, W2, W3, and W4. Now, the machine learning is the process of minimizing, or how we find our model. We minimize this loss function by finding a point from W1 to W4 that actually minimizes this loss function. And again, you're gonna see this almost in many slides, because we're gonna remind you that the same intuition that holds in multi-dimension is the same intuition that holds in two dimensions. As we approach a local or a global minimum, the rate of change gets closer and closer to zero. So if here we have 4 or 5 variables in two dimensions, we're going to have only one variable, which is x, but the same idea, the same intuition. Now let's talk about the gradient descent, but in multiple dimensions. So we have already described the idea of a multivariate function, and we have also talked about the idea of the partial derivative. So the idea is that for each variable in the loss function, we fix all other values, all other variables to a constant, and we keep one, and the result will be a function in terms of z, in terms of x, for example, and we do update that variable. So again, look at this diagram here, is that we started far from the minimum point, and because we are far, we actually we take a big move, and then we are moving gradually toward the minimum point in this function. Same thing applies in the multi-dimensions, but we take it variable by variable. When you take each variable separately, maybe the diagram will look something like this. Again, this is the intuition of that. Now let's see this in action. Let's see an example of this. So we have data. We have our model that says the weights 1 multiplied by the number of rooms plus the number of bathrooms multiplied by its weight plus a constant equal the price. So this is our model. And then there is the actual sale of a price the actual sale of a house that comprise the number of bedrooms, the number of bathrooms, and the price of the house. If we go here, so let's plug in these values. As we mentioned, we're gonna plug these data into the loss function. So we basically put 2 and instead of x1 in place of we're gonna put 3 in the place of x2, and 100 in the actual, and we're gonna put also 2 in x1, and we're gonna get a nice beautiful function in terms of w1, w2, and c.
Dr.
So
Khalid,
yes.
so this is the last function, right?
Yes.
And the C is the price or predicted price.
Oh no, the c is a constant, so any linear function is in the form of, let's say, f of x equal 5x plus 5. or 7x plus 7. This is just another variable in the in the linear model or linear function. It's like W0. You can imagine it as D0.
Oh, what's the cadence?
K, oh yeah, K, we put it here like 1,000. So for example, 100,000. We didn't want to put like three zeros. So you
Okay.
put K. Yeah, thanks for that question. Is it clear at this point? Do you think we should go back and explain more concepts or
No,
we are
I think it's clear.
okay, that's nice. So right now we have our beautiful loss functions. And again, how do we form our loss function after we choose the model? Here it is a linear model. And we apply that. We make the predictions, and each prediction minus the actual, and we square the value, and that gives us our loss function. And then once we apply the data set, that gives us a loss function in terms of W1, W2, C, and these are the values that we need to find so that we figure out and find our model. And these values must point us to a point in a diagram similar to this diagram that is minimum, where the rate of change is the rate of change will lead us to a point where the misprediction is very low or acceptable. Now let's try. So let's now we're going the next slide. We're going to try to see how we apply the gradient descent or weight updates in multi-dimensions. So as we've said before that this is our model, right? It's the same model, and the model will there will be an actual data where it will give us the actual price that the house was sold for, and then we will select W1. We're gonna update the W1 weight. So as we've said, as we've seen before, that when we take when we in a function with multi-dimensions, we fix all other values and we fix all other values and keep one as a variable. So here we will start, when we start the gradient descent, we start with a random point on this diagram, on this loss function. So here, let me go back here to this slide. We start with a random point because we need to start with a point. Can be random, can be anything. So we start with a random point, and once we apply it, we get a loss function or a squared function in terms of W1, and W1 is the weight we are going to update. And this process, by the way, we do it for each of the weights. So we do it for W2 and we do it for C, and every time we're gonna get an equation like this. But because this is the same process, we're gonna show it only for W1. Let's see how this is done for W1. So before we do that, we're gonna describe the chain rule because we're gonna use the chain rule to find the gradient. And remember, again, we were gonna keep stressing this. Uh, The value of the gradient tells us far are we from a minimum or a maximum point, and the weight gets updated to a value proportional to the gradient or the instantaneous rate of change. So that's why we need the chain rule. That's what we're talking about the chain rule. So the chain rule basically says in a composite function, the derivative of a composite function is the derivative of the whole thing multiplied by the derivative of what's inside. So let's take a look at the derivative of sine x squared. What is the derivative of the whole thing here? It's cosine x squared. What is the derivative of what's inside? It's 2x. And again, another example is f of x minus 7 squared. It is the derivative of the whole thing plus the derivative of what's inside. So what's the derivative of the whole thing? It is 2 multiplied by 5x minus 7, and the derivative of what's inside is 5. It's not difficult rule. You can read a little bit more about it. And in our previous lecture, we have pointed out to Highlights of Calculus series by Professor Gilbert Strang. We strongly advise to watch that series. You will get to understand these even in more detail. Now let's see how we update the weight. Once we have, again, now we have a function, in with one variable, and taking the derivative of function with one variable is easy. We know how to do that. It is a derivative of what's of the whole thing plus the derivative of what's inside. So it's 2 by 2W1 minus 45K. And this is applying this is basically that just the error. That's the difference between what you predict and the actual value. So for simplicity, we just keep it as prediction minus actual. And it is actually multiplied by 2. So if you look at this 2 that we put between brackets here, this is actually the value of the feature associated with that weight. So in this example, the weight update is we update the weight by multiplying 2 because you have a squared function by the value of the feature associated with that weight by the error. And the takeaway here is that, and we're going to be stressing on this, is when you update a weight with a value proportional to the gradient at that point, and we multiply by that something called learning rate. We have not talked about learning rate yet. We are just sneaking concepts into the presentation, but we will eventually talk about it. But right now, it's not that important to understand the flow and how the neural network learns. Assume it's just a constant.
So the W is the actual value. The gradient is the derivative plus the learning rate and times the learning rate, which is a constant, right? Or the variable, right?
Which rectangle are you talking about?
The last one, the conclusion.
This one, yeah. W is the weight, and
It's a current weight or the one that you recently derived.
so the one to the right is the current weight. The one to the left will be the new will be the updated weight.
And that updated weight, you will take it to the next step, right?
Exactly, yes. So
Okay.
that's a very good question. I like that question, Dr. Salim. Do you remember here when we say we start with the random points?
Uh-huh.
In the next step, we're not gonna start with the random point. We're
I
gonna
see. I agree.
start with the updated weights.
I see.
Dr. Salim, I like your paying attention. That's a very good question. Thank you for enriching that. Now, and I hope also the audience paying attention too. That's a very good. Now, shall we move to the next slide? Is there any questions here?
Nope.
Thank you. Now, there is another, we talked about activation functions and we emphasized them. And we have mentioned this activation function with this little formula here, which we did not explain. But this is not the only activation function. There is another activation function called ReLU, where if the signal is 0 or less, we're gonna assume that the signal is 0. Otherwise, the signal passes and is. And this function is abbreviated as max between 0 and x. So, and by the signal, we mean here, this signal, the combination of these little inputs over here, each feature by its weight, plus the number of RA hours by its weight, the number of papers by its weight, the number of courses by its weight, for example, X4 by W4. When we sum them together, we get a signal that is inputted to the activation function, and then the activation function processes and produces value. So in machine learning, there is a lot of activation functions, and there are benefits from using activation functions versus another, ranging from accuracy, for example, that affects the modeling accuracy of the neural network model. Some of them is better in computing power than others. We all hear about the massive training cost of generative AI. Some activation functions require less energy or implemented in less hardware than other activation functions. So basically, we're going to use ReLU activation function. And also it's very simple for the derivation of the neural network
So
that we're going to.
there is no like clear steps to choose one over the another. You have to just try them, right?
I think that's an area of research. Like when I started learning neural networks back, I think that was the command activation function. And then as they kept reading, they switched to this one. And they have even add a variation of this one. And they are using a different one for the generative AI. So it seems that depending on the task, maybe, and maybe they discover this one is more accurate, but it requires less computing power, right? Sometimes when they implement the neural networks in hardware, they might prefer another activation function for its simplicity or an approximation of activation function. Does that answer your question?
Yes.
Good. So this could be also an area of research too. We can look at this is a very fast evolving field. So what we know today might be obsolete. Not tomorrow, maybe the next half day. We're just exaggerating here, but this is a very fast evolving field. So now let's talk. Finally, we have reached the neural network. So I'm gonna say that gonna make a statement that up to this point we have all the math necessary to understand the derivation of the neural networks and how neural network learns. So let's recap what a neural network is. So a neural network is basically a connection of activation function. Each activation function receives signals from a previous layer and it produces another signal and it passes it to the next layer and the next layer, the next node in the next layer processes these signals. It's like a fully connected graph here. And once we know each of these links has a weight, as we have seen, for example, in predicting the research skills, it is predicted by the number of papers you've published. And it is the same thing. Once we know the weights, of these links, we are able to find our magical model that will help us predict. How do we find the value of these links? Basically, the neural network can be thought of and imagined as a big composite function. It's just a big composite mathematical function. So if you want to find the value, if we want to update this way, so how do we find the model? We start with a random point. That means we assign a random value to each of these links. And then after that, we take the partial derivative of the whole error function with respect to each of these links or with respect to each of these weights. And again, for example, here, if we want to see the green one, we take the partial derivative with respect to the green one. We're going to talk a little bit about math. Do we still have some time, Dr. Salim?
Yes.
Okay,
No,
a little bit. We're not going to too much math, but again,
we sorry, we have 3 minutes.
okay, the idea is to show that the math here is not scary because when people hear artificial neural networks and chain rule and partial derivative, they get scared. No, that's not scary. For example, in this last layer here, when you take the partial derivative with respect to this rule, this is exactly the same what we have done for the ReLU function. We're going to assume that all signals are above zero, are greater than zero. So for the purpose of simplicity, these equations here are the update to this rule is exactly the same thing that we have done here, the same derivation. So we've done this layer now. And so that's why I'm not going to go over these. We're putting them here for simplicity. Now, let's update this one. The only difference, or the only difference here, is that we treat this as a variable. The activation out of this node is treated as a variable. So we take the partial derivative of the error function with respect to a, and by the chain rule here, we take the partial derivative of the the error function with respect to a, and sorry, with respect to w1, and this equals the derivative of the error function with respect to a multiplied by the derivative of a with respect to w1, and that's the only difference. And will turn out this is 2 multiplied by the error value multiplied by the weight multiplied by the signal on S1. So basically, you can trace that on pen and paper, and it should not be that difficult. And the process of finding out the weights is called the backpropagation. And you don't need to study the backpropagation. You can figure out the backpropagation by doing partial derivative with respect to each weight, and you're gonna notice a pattern, and then that's how weights are updated. Now the mic, you have the mic,
Thank,
Dr. Salim.
thank you, Dr. Khalid, for this lecture. It's a very good lecture. I really appreciate it, and the audience as well. We don't have any more questions, and we are looking forward to see you again.
To see? Yeah, thank you, thank you. Probably next time we're gonna start the where to vector, which is that's the beginning. That's where we'll be touching the generative AI by explaining where to vector.
That sounds good. Thank you so
Thank,
much.
thank you so much, Dr. Salim. Nice
Okay.
talking to you.
Bye bye.